This is a short video presentation on identifying and quantifying gender bias in word embeddings and debiasing these word embeddings. Word embeddings can often propagate social biases such as those found in gender, race, or religion. This table shows some of the gender analogies that have been generated from biased word embeddings. This sort of behavior can often be undesirable, and it is often useful to remove this behavior. Now for some background on some of the terms that we'll be using throughout this presentation. Word embeddings are a way of representing words or terms using d-dimensional unit vectors. These vectors can have useful properties. For example, the difference between two vectors is analogous to the difference between those two words in natural language, often. Now, definitional sets. These are sets of words that define the bias subspace of the word embeddings. For example, he, she, man, woman, king, queen. Neutral words. These are the words that should not contain any gender bias. This is going to be the target of our debiasing. Finally, equalized words. These are these sets of words which we want to have equal components in the bias subspace. For example, man, woman, we would want these two words to be identical except for their components in the gender subspace, which would be opposite in direction and equal in magnitude. Now for identifying the gender bias. We'll be using the definitional sets, and for each definitional set, we will look at all the words in that set. We'll compute the mean of all those words, mu I, and subtract that mean from each word in that definitional set. And then we'll add each of these vectors to a matrix and compute the PCA of that matrix. The top k components will represent our gender subspace. In this case, we use k is equals to 1, so our top vector will represent our gender direction. For debiasing, there are two main methods that we'll use, hard debiasing and soft debiasing. In hard debiasing, there are two steps, neutralize and equalize. In neutralize, first we look at each word in the neutral set. We compute the component of that word in the gender direction, and then we subtract that component from each word and normalize. Second, to equalize, we look at the words in the equality sets. For each equality set, we compute the mean of the words in that set, and we compute the component of that mean in the gender space. We subtract that from each mean, and then we add back this term of gender component to each word in the equality set. Essentially, what this will do is make each word in each equality set identical except for their component in the gender subspace. Now for soft debiasing, our goal is to find a linear transformation T which we can do to our word vectors. This first Frobenius norm seeks to minimize the difference between the debiased word vectors, TW, and the original word vectors, W. The second term seeks to minimize the component of each word in the bias subspace, of each neutral word in the bias subspace. This parameter lambda simply weighs these two terms. To quantify our gender bias, we will simply be looking at a neutral set and computing the component of each word in the gender subspace, and summing those up and dividing by the number of words in that neutral set. Now to summarize our results, we can see that the biased embeddings received the highest score, which means that they had a higher component in the gender subspace. The hard debiased received the lowest score, and the soft debiased received a slightly lower score than the biased embeddings. The lower scores indicate that the debiasing was in fact effective, and hard debiasing was much more effective than soft debiasing. To summarize, word embeddings can propagate social bias, and it is often useful for us to debias them. The gender subspace can be found using PCA, and it can be debiased using hard or soft debiasing. Earlier results have shown that downstream utility is also conserved using these methods. So that is the end of this presentation. Have a good day.